So we're going to continue the discussion from a previous class, and today we're going to focus on the viscosity and the boundary layer itself to better understand what's really going on. First of all, just as a quick review of what we discussed last time, and you are more than welcome to pause this video and draw this or take a snapshot as you wish. What you can see in this problem is you have an airfoil. So you have an airfoil, and this airfoil has a flow that's coming. Uh, your stream is coming in this direction, so therefore the airfoil flow is going up and it's going down. And what's happening is the part of the flow that's actually very close to the surface is what we know this as the laminar flow. Okay, the part of the flow then when you start getting separated, right? This part over here that gets separated is when we know that's the turbulent portion of the boundary layer. And what's really happening here is outside the boundary layer. So this is the boundary layer itself. Remember, we defined the boundary layer as follows. We said the boundary layer was going to be the location where your stream actually ends up being constant, right? So this is your viscous boundary layer. This is the portion that we are really talking about. And in this part over here, the effects of the viscosity are confined to the boundary layer because depending on the boundary layer that I have, right, I can have a very large boundary layer. The bigger the gradient, the more turbulence I'm going to have. Okay, so this is kind of a summary of what we talked about last time. And there are a couple of ideas that I would like to fix before we move on any further. So the viscosity is very, very important in when we study aerodynamics. So let's summarize the effects of viscosity. And we call the viscosity mu. Okay, it plays an important role in the analysis of aerodynamics, and and the reason behind is the following. First of all, thanks to the viscosity, we have viscous drag. And you may wonder where that comes from. Well, the viscous drag, remember, your drag equation is nothing else than it will be your viscous stress multiplied by the surface area. So we know that your viscous stress is the viscosity times the gradient of the velocity respect to your distance y. Just remember when we have the boundary layer and you have a surface that's perpendicular to this, this part over here goes something like this. This is your y, and this is your stream velocity u. Okay, so there is du dy. Also, it is responsible for keeping everything in check between stall and separation. Remember what I told you last time. If there is no contact, if there's absolutely no contact of the fluid, then it's very dangerous. Then we're going to have separation. So what we are talking about is, let's say your lift versus angle of attack. This is what your plot looks like. And what I am saying is anything on this side, you can get very close to this, On this side, there is contact. Okay, there is contact between air and airfoil. There's full contact. Here is separation, and we don't like separation because the separation is going to make my airplane, the result of this will be my plane will stall. So if I don't have enough viscosity, I will eventually there will be a separation between the flow and the surface. And we don't like that. So the effect of viscosity is also responsible to make sure that we always have contact. Also, thanks to viscosity is that we have circulation. So viscosity creates circulation. It makes sure that the air is constantly flowing thanks to the viscosity. And a couple of more things that you have to understand. So for high Reynolds number again is defined as your density times velocity times length times mu. Another variation of this is you can know that this is the same thing as VL times nu, and this Reynolds number is a very, very important number that's used in almost any fluid dynamics, any fluid mechanics problem. This number tells me when I'm in I'm working with a laminar flow, I'm working with a turbulent flow, helps me decide when I have the boundary layer and when I don't have the boundary layer. So to better understand this, and you may want to pause and take notes on this. So if the Reynolds number is a dimensionless parameter, and we talked about this already, is dimensionless. And if the number is in the order of 0 to 100, then basically the viscous effect dominates. Because the viscous effect dominates, that means you're going to have a very large drag. Here is a low Reynolds laminar flow. In this region here, between 100 and roughly 1,000, you're going to have some separation, a bubble separation, but you're going to have reduced lift. You see, this is very, very important. And then here, whereas drag basically in this region becomes inversely proportional to E, here drag becomes proportional to my Reynolds number. Now, this is the region that we typically we want the aircraft to be flying, especially for high Reynolds numbers. You may talk something like this. Low Reynolds numbers, this is what's happening. And you have 1,000 to 10,000. You're going to have separation bubbles, decreased skin friction, and you have early separation. And we don't like that. And earlier stall. So this will be a case where all of a sudden you have discontinuous surface in the case that you have the airfoil and your flow is doing like this. There's a lot of separation. There are wakes that are formed here. So therefore you start having this separation. Okay, and we don't like this. So for high Reynolds number, basically we are talking this part over here. This is what ideal we like to see your airplane to flying. We want to see the airplane in the transitional region from 10,000 to 100,000, 1 million, I'm sorry, 100 to a million. And in this case, you're going to have both laminar and turbulent boundary layers. And if it's very, very turbulent, then you have the inertial effects take place, so the screnic friction gets increased. Here itself, you don't have too much separation. However, the increase of friction also increases your drag, which is not necessarily that good either. So with that said, uh, for high Reynolds numbers, let's write this down. For high Reynolds number, for high Reynolds number flows, let's say bigger than 10 to the 5, 10 to the 6. So we are in this transitional region. Viscosity is important. Inside the boundary layer. Okay? So all these are important concepts that we just need to understand. Another concept that's very, very important, and we talked about last time, but want to emphasize this a little bit more, is the idea of no slip condition. When I talk about no slip condition, we are talking about particles that they are allowed to stick to the body surface. So think about this. I have this, and I have a small particle of fluid. The particle of fluid now is just moving all the way across. My surface doesn't even know the particle is moving because it doesn't even stick. There's nothing happening between that particle at time 1, let's say, and this particle has moved to a position time 2, but the surface that's standing here has no clue what's happening. The only way the surface can really know that something is happening here is if actually the fluid particle hits the ground, hits the surface. When it hits the surface, now it creates the boundary layer. So it's going to create this boundary layer, and this is when your surface really knows, hey, something is really happening. Okay, so let's talk. Let me write down. This is no slip condition. Okay, so fluid particles in a viscous flow, because we have some viscosity. Remember, the fluid has viscosity. Basically, stick to the body surface. Okay, so what we are really doing is we are saying because it sticks, right? Because my particle is sticking to the surface, it's sticking, there's no slip condition, it sticks there in that particular time where the small particle is, change this a color. This small particle, sorry, is sticking to the surface. In that very condition, very moment, the total speed, total speed at the surface is equal to 0. Now, this is what happens in a non-slip condition. Now, consider the case in which, let's contrast it with an inviscid flow, where the particles are allowed to slip. So this is a no-slip condition when Uh, then we have the opposite of that is the inviscid flow. In the case of the inviscid flow, particles are allowed to slip past the wall. Okay? So let's have the two conditions here. Let's compare one with the other. The first condition, let's call this inviscid. Let's call the second condition viscous. So if it's viscous, we are assuming that the particle is sticking. Okay? So here, what we are saying is that it is allowed to slip, but it has to have contact. Okay? So we have your small element there. Your element is allowed to keep moving, and it keeps moving. Your surface doesn't really, there's not much of interaction between the flow and the surface. The surface, you can think like the surface doesn't even realize there's something happening. So in this particular case, when it passed this wall, in this case, you can show that if I take the dot product of my normal, this will actually give me 0. It's completely perfectly 90 degrees here. That's why you get orthogonal, 0. Now, in the viscous case, there's the inviscid flow. This is the viscid flow. For the viscous case, I don't want the slip. I don't want it to slip. So now you have this small particle. Because I don't like it to slip, I want it to stick. What it's going to try to do is it's going to create a boundary layer, right? And this boundary layer is going to look something like this. And what's going to happen is at some point here, okay, call this delta. So it's not perfect. It should be completely the same distance from here to here. This is the boundary layer. Okay. And your flow is moving in this direction. This is your U. This is your Y. Then at the wall, here at the wall, you're going to have mu du dy at the wall. Okay? So this is the case of an airfoil. I got the same point. I can have the same point, maybe somewhere over here acts more like inviscid. Somewhere here acts more like viscid, like a viscous flow. This one acts like more like inviscid flow. That's why when I started my earlier discussion, I just told you this. I told you this plot, and when I explained this plot to you, I told you this is what's happening here. This is inviscid. This part over here, but typically this is the flow. The flow keeps moving. In this part over here is laminar and turbulent. So you have a viscous flow acting here. And then this over here where there's a separation is inviscid flow again. There's not so much of a contact. And what you see here, this surface that you see here, this is the basically viscosity. You can see the separation of the flow. There's more separation of the flow here than over here. Here's the full contact. Okay? So we talk about those transition regions because they are important. So that's why your Reynolds number becomes very, very important parameter. I know this sounds a little bit abstract and hard to understand, but all you have to know is the Reynolds number. That's the density, the speed of the stream times the length divided by my viscosity. That's going to give me Reynolds numbers and is dimensionless parameter. And I want to make sure that for my problem, you remain somewhere over here. Now think about this. How can I make this happen if I'm designing the aircraft? Well, I have to control how much. I know the dimensions of the aircraft, and since I know the dimensions of the aircraft, I can determine how much faster the plane is going to go, how much slower it's going to go, and the faster it's going to go, or even if I go higher, I can go lower. I can control the I can control, if I go higher, I can go lower. I have the ability to control the density of my stream. And then also I can control how long my span is as well. And so that's why when you're analyzing these problems, any of these combinations can help you can achieve to make sure that you are around the transitional region. Okay? Okay, just as a summary, going back to this picture from your textbook, what you can see is this is inviscid flow because in this region there's nothing that's sticking. So you basically your fluid is completely from this region is completely moving a particle here. However, as you get closer to this, the boundary layer is a viscous flow. Basically, what we are trying to do and we are trying to say is, here I have a small particle here, and you just keep on going to go. It doesn't touch this. But I can have another particle here. Now this one is actually in full contact. It's creating the viscous flow. And many times your velocity, the velocity gradient is equal to this nice parameter. But don't worry about this. We'll talk a little bit more in detail about that later as we move on. So let's go back to this chart here. And let's focus all our attention now to what happens in the transitional region. Okay? In this transition region, many things happen. And so let's see what happens. Let's see how does your fluid actually behaves and what really happens. First of all, let's suppose this is the surface of the airfoil. We're going to model this as a flat plate. Okay, just for the sake of this example. And we're going to say your y goes in this direction. And you have a fluid flow coming in this direction, u. Okay, so what's going to happen is if I take a very small particle now, the particle is moving and it's going to keep moving, and eventually at some point, so it's keep moving up to a point here. Talk about what happens there in a moment. At some location here, what's going to happen is your particle is going to start to develop, it's going to start acting like a viscous fluid, okay? So now you're going to have your nice gradient, you're going to have viscosity. So somewhere between this point, let me change the colors for a moment. Somewhere between this point and all the way here, this is basically laminar flow. Okay. And then yes, maybe I should have drawn this, or probably it's easier just for me to change this. Somewhere here is closer to this point. This point right here, this location from here, this is a location in X that where my laminar flow really starts. And this is the location, this is what we call L critical. The total distance that's actually going to move. And from this point on, what happens is this region right here has a value of Reynolds number. Remember, rho times U times L critical divided by mu will give you about 200,000 to 10 to the 6. And beyond that region, this is what's going to start to happen to your flow. Your flow is going to start to do this. So now you're going to have lots of wakes. You're going to have vortices that's going to generate in here. You have vortices. And then these vortices that generate inside this are called wakes. And because of these wakes, this whole region becomes turbulent. Okay. And you can immediately see that if something is very turbulent, it's not necessarily a good thing. We don't like that. And we're going to call that, let's say, an arbitrary distance. I'm over here. I can call this letter L. Okay, so then your Reynolds number anywhere here would be rho times mu times L divided by mu. Okay, that's how we define that. Now, many things happen in one region and the other. First of all, as you can see, as you probably can guess, anything from this side and here is laminar. So it's beautiful, it's nice, it's a smooth ride. So everything here basically becomes steady. So we don't have to worry about time. Everything here is unsteady. So this is unsteady, and time becomes now very, very important. So everything is a function of time. Here, this is time is independent. There are a couple of things, many other things that really happens in these regions. So let's go ahead and separate. Let's go ahead and explain this better. Okay. So in the laminar flow and the turbulent flow. First of all, as I just mentioned, your flow is steady and is unsteady on this side. Okay. The flow grows slower. Here grows faster. This is an emptier profile, fluid profile, emptier profile. Remember, we are talking about the air. This is a fuller, if we can use that word, profile. Here, mainly there's friction, there's a lower skin friction. Here we have a large skin friction. So let me ask you this. If we don't like turbulence, turbulence creates more drag, but if this has a lower skin friction, this one has a larger skin friction, which of these two will separate easily? Anyone? Do this again. This has a very small skin friction. This has a large skin friction. which of these two it will stick easy? The one that has large. So this one, very good. This one will resist separation. And this one separates easily. And so, although we don't like the drag, but here I can ensure that my fluid is actually sticking to the surface. Here I know that it will separate. And you can see from the picture I just drew, right? You can see that in this, somewhere in this region over here, you don't have any airflow air actually sticking, because it's just starting as my velocity starts increasing. Then, so think about this. I got this, and I put a big fan here, and I'm going to start to blow my wind. Okay, so my air is starting here at 0, and it's going to keep on growing. It's going to go faster, 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 faster. And as it's going very slow, there's nothing happening in this region. There's absolutely nothing, because there's all full separation. Then here, this is viscous flow, and this is inviscid flow. You don't have that much. Your fluid doesn't stick there, right? So another thing that's very interesting to understand is what happens to the boundary layer as my mu increases, right? So again, let's assume I have a skin thickness. I have a boundary layer, I'm sorry. And let's say my boundary layer, a typical boundary layer looks something like this. So this has a mu, okay? And this is at a velocity v. So now what happens if I increase my nu? If I increase the value nu, this is what happens to my flow now. If I decrease my mu, this is what happens to my flow. Everything is going to end up in the same spot. Ends up exactly on the same spot, if you would. This was your original flow. Let's call this our base mu. So as my mu increases, you can see what happens to the boundary layer thickness. Here, the boundary layer thickness is here, delta, okay? But here, my boundary layer is all the way over here, delta 2, okay? So what I am saying is my boundary layer thickness, the BL is for boundary layer thickness, and we're going to call this thickness delta, okay? So if this is small, delta will be small. If mu is big, delta will be big. So depending on the viscous property of my fluid, the viscosity of my fluid, I can control how much of the boundary layer I'm going to have. What's going to be the size of that boundary layer. Okay? So if I keep studying this and understanding what's going on here, one of the things that we discussed last time, I just gave you the stress, but let's go a little bit in detail to understand what's really happening. And we have been talking about the stress all along, but I think it's worth to stop for a moment to understand the consequences of this. The stress, the viscous stress, at the boundary layer. So I'm saying I got the boundary layer, I got the wall, this is your wall, okay? And your stream is measured in delta. And now you have basically, you're going to have a slope that's going to go right there, and it's going to go, oh my gosh, it's going to do something like this. Okay? And so what we are saying is this slope that takes place here is du d theta, and you can immediately see that the slope is going to determine the size also of my delta. You see? So as one thing you can see here, what happens when your mu approaches zero? If your mu approaches zero, let's see what happens. Your du dy at the wall is tau over mu. This goes to zero, so this tends to infinite. So mathematically, it's saying this is completely infinite, but the consequences of this are, what this is really saying is, the only way this is infinite, if this is going to zero, I also know that my Reynolds number that's equal to rho u L mu is also going to tend to zero. It's also going to tend to infinite, if you realize, right? But this is zero, this is also going to go to infinite. So what does that really mean? It means that if this goes to infinite, means that your boundary layer is actually almost horizontal. This is what's happening to your boundary layer, it's almost horizontal. So if it's happening like this, it's saying, hey, you basically, this is infinite. It's a habit there. I'm sorry. It's going all the way up. All you're saying, basically, all your flow that you have is turbulent. Okay, you have an infinite Reynolds number. One way to understand this concept, or understand what's really going on in here, is the following. So let's fix some thoughts here again. If this is zero, we know that your tau will go to infinite. And as a consequence, we also know that your Reynolds number goes to infinite. Okay? Where your L is basically a fixed value, because I know the distance over my body, that's my L. So I know this is fixed. And I know that my Reynolds number is nothing else than rho u L over mu. Okay, so if I did this problem, I can also write my Reynolds number in the following form. Rho, let's call it v, the speed, mu. If I multiply top and bottom is by a 1, right? I can multiply by 1 and get the same number. This will give me rho v squared. At the bottom, I will get mu b over L. Okay? So basically, what you're saying is this, what happens at the top is nothing else than the inertia forces. This is the inertia force. What's happening at the bottom is the viscous force. So if I'm saying this is going to infinite, I'm saying that now either you have infinite inertia forces or you have zero viscous forces. So that's what we are really trying to do. And this is what's really happening here. Now, do we want this to be zero? Of course not. We don't want, this can never be infinite, then you have infinite drag. That means I have infinite inertia inertial forces. I have zero viscosity, which I not necessarily good either. So there is a balance between all this. Um, please stick with me. I know this concept is kind of hard at beginning as you're seeing this for the first time, but I want you to again think about a flat surface. You got a fluid that's moving all the way across, and as the fluid is moving, no slip condition, okay, that has to stick at the bottom, has to stick here, and has to move. And then if that's the one case, the other case scenario, the other case that you're going to have is the case that when you have the fluid moving is sticking, the other one is not sticking, so it's in viscid flow, it goes all the way across. We want to have some turbulence. Too much turbulence, infinite turbulence is bad, but some turbulence I need it because turbulence actually helps my fluid and my surface to stick together. Okay, I want it to stick. So when we are talking about all this, something else that has to come to better understand what's really happening here in this scenario, so you can better understand what happens. Consider this. Let's suppose L can be, in this particular equation, L can be many different sorry about that. So I told you got your Reynolds number. That's rho V L mu. Okay. Let's see what is your L. So we know the rho is the density. We know that V is the velocity. We know that mu is the viscosity coefficient. But then let's see what is L. L is the characteristic length. And that characteristic length can be any of these lengths. Can be the chord. This is for the case of airfoils. It can be length, total length. This is for bodies, maybe plates. Or it could be the diameter for circles and spheres. Okay, so what we are saying here is that I have the option of designing my plane. If I'm designing a plane, I'm designing the chord of the airfoil. I can make the airfoil as wide, as large, as small as I want. In controlling that, I control my Reynolds number as well. Let me give you an example. Like for an example, let's suppose I have, let's compare two cases. Let's consider a small airplane, maybe a Cessna type of model, a 6-passenger plane. Here, your Reynolds number is about the range of 10 to the 4. It's about 10 to the 4, maybe 10 to the 5. But a Boeing 747, on the other hand, is to the order 10 to the 8. Sorry, 10 to the 4 and 10 to the 8. So this is what you have for your Reynolds number. I cannot do my math today. I'm so sorry. 10 to the 5, 10 to the 8. So what you do in the airplane, when I'm designing the aircraft, if I look at the aircraft from the top, right? and you got your wings. So what I can do with my airplane, I have the option of deciding what's the length. You're going to see that obviously your Boeing 777 is going to have a longer chord, a larger chord than its counterpart for a smaller airplane. And everything that we are trying to do is we are trying to design the plane. If I want to have too much contact of the flow and the plane, or I want to have a less contact the airflow, airplane and the flow. And then from here, so if I gave you something like this, and you know that already this is laminar flow, this is turbulent flow. Turbulent flow. And what we want to find here is this L critical, so I can stay somewhere in this region. Okay. So basically, this is the whole idea how this is designed to make sure this is working. And this point right here typically is at 200,000 to probably 10 to the 8 power. And that's what happens with small airplanes and large airplanes. That's the consequence of that. Okay. So when I'm designing my airplane, to know something that's laminar or is not laminar is highly, highly, highly important. And that's going to determine the value of my drag. So it's going to tell me the value of my drag. It's going to tell me the value of my, obviously it's going to affect my lift as well. But this one is going to just tell me the value of my drag. That means I may need to have a larger lift to overcome the drag that is causing that. But I may need to have that viscous drag because I may need to have a better contact of the surface. So a larger plane versus a smaller plane, you can see how the Reynolds number plays a big role into that. Okay. To wrap up this discussion here, let's see what is the thickness of the thickness of my boundary layer. So for a laminar boundary layer and a turbulent boundary layer. Turbulent boundary layer. So here, your boundary layer is going to be approximately times L square root of the laminar Reynolds number. Here is going to be 0.37 L REL to the 0.2. So if I'm going to compare, this one is 5.2 L. This one is REL 0.5. You can see that this number is going to be smaller than this one. So this number has your delta will be larger for turbulent boundary layer. These are approximations that typically happen in a typical aircraft. And this basically wraps up all our discussion for turbulent and boundary layers. So the only reason we have the discussion is to understand how the aerodynamic forces work. Again, and keep emphasizing, I want to make sure that my plane flies, right? My plane, in order for my plane to fly, so in order for my plane to fly, I told you that no air, no motion, no air, no lift, so therefore my plane doesn't fly. But at the same time, I'm telling you, you're going to have a drag. and the drag is going to depend on how much viscosity is going to be there. And one of the viscous terms, one of the drag terms has many terms, and the first term is the viscous drag. That one we cannot avoid. Design the aircraft to have a certain value. I could do that. So our goal when we are designing an aircraft, or the aerodynamicist when it's giving a shape to the aircraft, has to determine how much drag is it willing to live with. And based on that, then you have many wind tunnel testing or computational fluid dynamics nowadays, CFD, over my airplane to understand where the wakes are. Can I reduce the wakes in some cases? If I can, awesome. But I want to make sure always my fluid is, my fluid is sticking to the plane. Otherwise, my plane will stall. I lose the performance of my aircraft. So this is the whole discussion and the whole importance of viscosity and boundary layers.